Run wild, run free. The skies beneath our feet. Run wild, run free.
Food is a major part of our daily lives, and almost everyone loves to eat. But for the people who don't, how the heck do you survive? While humans primarily eat for pleasure or because they can't work on an empty stomach, food is also a key ingredient in the recipe for survival. Going to the fridge or the grocery store is simple enough. But when you're in the middle of the forest, at the bottom of the sea, or the peak of a mountain, things get difficult pretty quickly. Animals live through this each day, and that's precisely what we're tackling today. So, sit back, relax, perhaps get a snack, and let me introduce you to the complicated yet interconnected world of ecosystem dynamics. Let's start off simple. Animals, like all living things, need energy to survive. There's no such thing as an animal that doesn't eat, because without energy, life stops. It's like trying to run a phone at 0% battery. It just doesn't work. A food chain is a linear progression of who eats who. We start off with a producer, which gets energy from the sun, such as grass. That grass is consumed by a first level or primary consumer, like an eastern cottontail rabbit. After the rabbit, we get a second level consumer in the form of a predator, such as a red fox. The fox will catch the rabbit and eat it. That's a very basic food chain for you, but it can go even further depending on what consumers are involved. Let's try another example. A grasshopper might eat a leaf. A mouse would eat the grasshopper, which would be consumed by a snake, and finally would be snatched off by a red-tailed hawk and devoured. Great, they got a meal, then became a meal. So, what does this actually tell us? First, we can identify the feeding roles. The grasshopper is a herbivore, just like the rabbit. The mouse is an omnivore. It eats both plants and animals. Then come the carnivores, the predators that sit higher in the chain. Notice how the hawk doesn't get eaten. This is because it's what's known as an apex predator. Apex predators don't get preyed upon by other animals in their ecosystem. Below them, you might find mesopredators, just like the fox, which can hunt smaller animals, but may also be hunted by larger predators. Every animal has a role in the ecosystem, which we refer to as a trophic level. Second, these chains show how energy moves through ecosystems. Each organism takes in energy by eating, but not all of it gets passed along. Most energy is used for movement, growth, and life processes, or lost as heat. In ecological terms, we call this the 10% rule, which states that, on average, only about 10% of energy is transferred from one trophic level to the next. The rest, about 90%, is lost as heat or waste. So, if a plant starts with 100% of the energy, a grasshopper gets about 10%, a mouse gets 1%, a snake gets 0.1%, and a hawk ends up with just 0.01% of the original energy. Yes, I did the math. This is why ecosystems can't support endless top predators. They simply don't get enough energy. So, that's a food chain. But you now might be wondering what a food web is. Buckle up. A food web is what you get when you zoom out from a single chain and see the full picture. Real ecosystems don't work in straight lines. Instead, they function more like interconnected networks where energy flows in multiple directions at once. At the base of every food web are producers. Plants like grass, trees, and berries. These organisms convert sunlight into energy through photosynthesis, acting like living solar panels. Above them are consumers, which include herbivores, omnivores, carnivores, and insectivores. For example, a grizzly bear might eat fish, deer, roots, and berries depending on availability. This flexibility allows ecosystems to remain stable when conditions change. A food web accounts for the fact that most animals eat more than one type of plant or animal, which helps scientists predict how the removal or addition of a single species might impact the entire habitat. The catastrophic removal of a species can trigger a trophic cascade. Each trophic level suffers from the removal of a critical component of the ecosystem. To understand this, we can look at Yellowstone. In the mid-1900s, wolves were removed from Yellowstone National Park. At first, elk populations increased significantly. Without pressure from predators, they overgrazed willow and aspen along riverbanks, preventing young plants from regenerating. That vegetation loss affected the rest of the ecosystem. Birds lost nesting sites, beavers lost building materials, and river systems changed as banks became less stable. A single change at the top cascaded through vegetation, wildlife, and even physical geography. Now, let's reverse the situation. If herbivores like elk are removed, vegetation expands rapidly, forests thicken, and riverbanks stabilize. But this can also reduce habitat diversity and allow some plant species to dominate while others disappear. Predators also lose their main food source and may decline or move away. In this sense, herbivores act as a balancing point in the ecosystem, regulating energy flow between plants and predators. At the most extreme level, removing producers collapses the system entirely. Without plants, herbivores lose their food source, followed by predators losing theirs. Energy input into the system shuts down. In Yellowstone terms, without grasses, willows, and aspens, elk would disappear, followed by wolves, beavers, birds, and insects. This represents a bottom-up collapse, and it is the hardest type of ecosystem disruption to recover from, because the entire energy foundation must be rebuilt before higher levels can stabilize again. Whether change starts at the top, middle, or bottom, ecosystems adjust through interconnected feedback rather than isolated events. In the Yellowstone story, wolves were heavily demonized for decades. These incredible social creatures were seen as dangerous threats, villains that needed to be removed to protect livestock and game animals. That mindset led to their complete elimination, but removing them created unintended consequences. Without wolves, elk populations expanded rapidly, vegetation along rivers was overgrazed, and entire landscapes began to shift. What was meant as a solution ended up destabilizing the ecosystem. This is where ecology pushes back against human storytelling. Nature doesn't operate in terms of heroes and villains. Wolves aren't evil for hunting. Elk aren't wrong for feeding. And plants aren't victims or heroes. They're all simply part of an energy system, each responding to the pressures of survival. At the same time, treating ecosystems with total indifference, ignoring these relationships entirely, can also lead to disruption, because every action still affects the system, whether we acknowledge it or not. In the end, Yellowstone shows something simple but important. Ecosystems are connected networks, and every role matters. When we assign morality to nature, we miss how it actually works. And that concludes today's video on food chains, webs, and trophic dynamics. Thanks for joining me. If you're into wildlife, ecosystems, and the wonders of nature, stick around for more explanations about the natural world. Please feel free to subscribe as well. And, of course, remember, to be wild means to be free.